TRG-planner. Traversal risk graph-based path planning in unstructured environments for safe and efficient navigation. Legged robots are becoming powerful tools for autonomous navigation across unstructured terrains, places where wheeled robots simply can't go. However, when navigating such environments, most existing methods classify terrain only into free or obstacle space. This binary classification is far too simplistic. It ignores how terrain characteristics like slope, roughness, or elevation can change traversal difficulty or even safety. To address this, traversability maps have been widely adopted. These encode terrain safety or difficulty in a geometric sense. But there's still a critical gap. They usually ignore directional relative risk and terrain reachability. In other words, traversability maps tell where it's safe, but not how risky it is to move from one region to another. To tackle these challenges, we propose the Traversal Risk Graph, TRG, as a novel framework for path planning in unstructured environments. TRG is a graph structure that models both terrain reachability and the relative traversal risk between connected regions. It operates in a hierarchical manner with global and local graphs, allowing real-time updates and scalable planning. Finally, our risk-aware cost formulation enables safe and efficient navigation, even in unknown environments. TRG node corresponds to a terrain region that the robot can stand on safely. To determine stability, we compare each cell's height value with the median height of the terrain. This allows the planner to evaluate local flatness and reject unstable areas. Also, nodes are only valid if they are reachable and have at least one connected edge. And each edge of TRG represents a path candidate between two nodes. We model each path candidate as an ellipse plane, extracting its principal directions using PCA. The relative traversal risk is then derived from the geometric properties of the plane. For example, steep or highly uneven transitions lead to higher risk scores. Then, how is TRG generated and maintained? The graph is built incrementally, inspired by wavefront propagation. It adds new nodes in unexplored regions and merges nearby ones for efficiency. Due to this incremental initialization, TRG can be generated over 9 times faster than conventional graph generation methods, PRM*. Additionally, TRG maintains both a global graph for long-term planning and a local graph for immediate updates. Only the local graph is updated when the environment changes, and in unknown areas, only the frontiers of the local graph are expanded. This hierarchical approach keeps computation scalable and allows real-time ray planning. Finally, we formulate a graph optimization problem on the TRG. The cost function balances path safety and travel distance, enabling efficient and risk-aware navigation. In simulation, the TRG-based planner successfully generates multiple paths according to the safety strategy, achieving higher success rates and faster planning compared to baseline methods. Furthermore, TRG-planner successfully achieves safe navigation in several real-world environments, including mountainous terrain and the QRC arena. Depending on the safety strategy, the robot either follows a safer but longer path or a riskier but shorter one. It also supports mapless navigation, continuously updating and optimizing the path in real time. TRG is incrementally expanded toward unknown goals, allowing the robot to explore unknown areas. Even when dynamic obstacles appear, TRG-planner can replan the path through real-time graph updates, ensuring safe navigation in changing environments. In summary, TRG-planner bridges the gap between geometric traversability and risk-aware decision-making for legged robots. Thank you for listening. Please visit our project website for more details.